As you find a comfortable place to rest this evening, let your mind drift away from the immediate concerns of the day and settle into a story about how we came to understand the quiet, hidden machinery of the world around us. Right now, in this very moment, millions upon millions of invisible particles of light are raining down upon your skin, washing over you in a silent, ceaseless tide. Each one of these minuscule packets of light is performing a quiet, profound impossibility that has baffled the greatest minds in human history. Every single photon is acting as both a solid particle and an expansive wave at the exact same time. It is not alternating back and forth, and it is not choosing one nature over the other depending on the circumstances. It is inhabiting both realities simultaneously, without exception or compromise. No one, from the towering intellect of Albert Einstein to the brilliant curiosity of Richard Feynman, nor any physicist working in a laboratory today, can provide a complete, intuitive explanation for why this should be. They can write down magnificent equations that describe it with breathtaking precision, predicting outcomes to many decimal places, but they cannot explain it in the simple, comforting way you might explain why a stone falls when you let go of it. This is the heart of quantum mechanics, a theory that stands as the most thoroughly tested and overwhelmingly successful framework in the history of science, yet rests upon concepts that feel entirely alien to our everyday experience. These were ideas that the very people who uncovered them fought against, concepts that triggered decades of heated debate, dissolved personal friendships, and forced generations of scientists to completely redefine what it means to truly know something. Yet this strange worldview did not materialize out of nowhere in a single blinding flash of insight. It was constructed slowly, brick by brick, over a span of about 30 years by a small group of researchers who were initially just trying to solve very practical, unglamorous industrial problems. They were looking at mundane things like ovens, heating elements, and the way glowing metals change color as they get hotter. The answers they stumbled upon were so uncomfortable that many of them spent the remainder of their lives trying to find a way back to classical certainty. This is the tale of how those pieces came together, showing how reality at its deepest level is far richer and stranger than our everyday intuitions could ever prepare us to imagine. To understand where this journey began, we have to travel back to the late 1890s in Germany, where physicists were consumed by an enigma known as blackbody radiation. The concept is straightforward enough if you imagine a completely sealed hollow metal box, like an industrial furnace or a ceramic kiln, heated until it glows. As the temperature climbs, the interior light shifts through a predictable sequence of colors, starting with a dull cherry red, moving through bright orange and yellow, and eventually reaching a blinding white-hot brilliance if the heat is pushed far enough. Everyone who has watched a blacksmith work iron or stared at the glowing coils of a kitchen stove has witnessed this transformation firsthand. The burning question for scientists at the time was whether they could construct a universal mathematical equation that could precisely predict the exact spectrum of light wavelengths emitted by such a glowing cavity at any given temperature. This was far from a purely academic exercise. Germany was undergoing rapid industrial expansion during this era, and there were significant commercial interests at stake. A government agency known as the Physikalische Technische Reichsanstalt was actively funding research into thermal radiation because the booming gas and electric lighting industries desperately needed standardized measurements to manufacture better lamps. Because real money and national prestige were tied to the outcome, some of the most talented experimentalists in the world were painstakingly measuring the light pouring out of carefully calibrated furnaces. Their experimental data was pristine, yielding smooth, reliable curves that mapped out the energy output across different colors. The crisis lay not in the measurements, but in the inability of existing theory to account for them. The established physics of Isaac Newton, James Clerk Maxwell, and Ludwig Boltzmann produced a prediction that was catastrophically wrong. When classical theory calculated how energy ought to be distributed among the various wavelengths inside the heated box, the formula worked reasonably well for long wavelengths in the red and infrared regions. However, as the calculations shifted toward shorter wavelengths in the ultraviolet range, The mathematical prediction diverged wildly, shooting straight up toward infinity. According to classical physics, a hot oven ought to radiate an infinite amount of energy in the ultraviolet spectrum, a clearly absurd conclusion that would mean opening a kiln door would instantly incinerate the room in a flash of invisible light. This glaring contradiction became known as the ultraviolet catastrophe, signaling a profound and undeniable breakdown in the foundations of classical thought. It was not a minor discrepancy or a sloppy rounding error, but a complete structural failure that defied every conventional remedy. Several prominent researchers attempted to bridge the gap. Lord Rayleigh and James Jeans formulated an equation that captured the long wavelength behavior while spawning the infinite divergence at the short end. Wilhelm Wien developed a competing formula that behaved nicely in the ultraviolet but failed completely in the infrared. Physics was left holding two conflicting maps of the same territory, neither of which could describe the whole landscape. Into this intellectual stalemate stepped Max Planck, a figure whose personality and worldview make the ensuing revolution all the more remarkable. Born in Kiel, Germany in 1858, Planck was a man of deeply conservative intellectual habits. He cherished order, revered classical thermodynamics as an almost sacred edifice, and believed firmly in the absolute, continuous laws of nature. He was temperamentally unsuited to tearing down the pillars of established science and would exhaust every conventional avenue before even glancing toward a radical solution. Yet, by the autumn of 1900, after years of wrestling with the black-body problem, Planck found himself cornered. On the 19th of October, 1900, Planck presented a new formula to the German Physical Society, a mathematical expression he had arrived at by skillfully interpolating between the Wien and Rayleigh-Jeans equations. When experimentalists tested his new formula against their laboratory curves that very night, the fit was astonishingly exact. Heinrich Rubens called Planck the next morning to confirm that the mathematical expression matched the data across the entire spectrum without a single flaw. The triumph of having the right formula was immediately overshadowed by a deeply unsettling reality. Planck had no idea why it worked. He possessed the correct mathematical description, but he lacked any underlying physical justification or derivation from first principles. Over the next 2 frantic months, he worked backward, searching desperately for the physical assumption that could force his equation into existence. The answer he finally uncovered disturbed him deeply. The only way to derive his formula mathematically was to abandon the assumption that energy is continuous and smooth. In classical physics, energy was thought to flow like a liquid stream, infinitely divisible down to the smallest fraction, allowing for any conceivable quantity along a continuous number line. Planck discovered that to make his equations hold true, he had to assume that the microscopic oscillators in the walls of the heated cavity could only emit or absorb energy in discrete, indivisible packets rather than a continuous flow. He referred to these fundamental packets as quanta, drawing from the Latin term for how much. Crucially, the magnitude of these energy chunks was not arbitrary. It was directly proportional to the frequency of the light itself. Higher frequency radiation, such as ultraviolet light, came bundled in much larger packets, while lower frequency radiation, like red light or infrared, arrived in smaller packages. The relationship was elegant and simple. The energy of a single quantum was equal to the frequency multiplied by a fundamental constant, an unimaginably small number that ensured the chunkiness of energy remained entirely imperceptible in everyday life. Planck designated this proportionality factor with the letter h, which posterity would name Planck's constant. Its numerical value was exceedingly small, characterized by a decimal point followed by 33 zeros before reaching a significant digit, yet it was distinctly greater than 0, and that tiny non-zero value changed everything. To picture this difference, imagine the contrast between walking up a smooth, inclined ramp versus climbing a staircase. On a ramp, you can pause at any continuous height you choose, while on a staircase, you are strictly limited to standing on specific discrete steps. In the macroscopic world of human experience, energy resembles a ramp, flowing smoothly and continuously. Planck was proposing that at the atomic scale, energy actually resembles a staircase, with steps so impossibly minute, that they blend together in normal observation. However, when dealing with individual atoms and high-frequency radiation, those individual steps become immensely consequential. The ultraviolet catastrophe vanished under this new perspective because at very high frequencies, the required energy steps become so massive that thermal agitation cannot readily supply them, choking off the emission and preventing the infinite energy divergence that plagued classical theory. Despite unlocking this monumental secret, Planck did not believe he had uncovered a fundamental truth about the architecture of reality. He viewed his introduction of discrete quanta as a clever mathematical trick, a computational artifice that someone else would eventually replace with a proper derivation rooted in continuous classical physics. He famously described the move as an act of desperation, undertaken because a theoretical explanation had to be found regardless of the cost. He spent years afterward trying to strip the quantum hypothesis out of his work, hoping to restore continuity to physics, but he never succeeded. The man who unintentionally launched the quantum revolution spent much of his later life wishing he could take it back. The containment of this radical idea lasted only half a decade. In 1905, a 26-year-old patent clerk working in Bern, Switzerland, took Planck's concept of quantization and pushed it in a direction that Planck himself found unimaginable. Albert Einstein recognized that while Planck had restricted energy quantization to the emission and absorption processes occurring within matter, the implications ran much deeper. Einstein proposed that light itself is fundamentally particulate in nature, traveling through space not as a continuous wave, but as a stream of discrete energy bullets, with each individual packet carrying exactly one quantum of energy proportional to its frequency. Einstein did not offer this as a purely speculative philosophy. He used it to solve a stubborn experimental mystery known as the photoelectric effect. Discovered nearly 2 decades earlier by Heinrich Hertz, this phenomenon occurred when ultraviolet light shone onto a metal plate, causing electrons to be forcefully ejected from the surface. While the general ejection of electrons made sense under the assumption that light delivered energy, the specific details defied classical wave mechanics. According to wave theory, a brighter, more intense light wave should deliver more total energy, meaning that even dim light would eventually build up enough energy to knock electrons loose if given enough time, and brighter light should knock them out with greater speed. Instead, experiments showed that the energy of the escaping electrons depended entirely on the color or frequency of the light, rather than its brightness. A very dim ultraviolet lamp could successfully knock out high-speed electrons immediately, whereas a blindingly intense red light could shine on the metal indefinitely without dislodging a single electron. Einstein demonstrated that if light is composed of discrete packets, this behavior becomes immediately transparent. A single photon strikes a single electron in a direct interaction. If that individual photon possesses enough energy, which is determined by having a sufficiently high frequency, it successfully liberates the electron on the spot. Increasing the brightness of the light simply increases the total number of photons arriving, producing more ejected electrons without altering the individual energy imparted by each photon. Red light, possessing a lower frequency, carried insufficient energy per photon to dislodge an electron, rendering intensity irrelevant because individual photons lacked the necessary punch. This revolutionary paper earned Einstein his Nobel Prize in 1921, serving as an official acknowledgement of the particulate nature of light, even if his theory of relativity was still considered too controversial for the committee at the time. Yet, despite its explanatory power, the idea of light quanta met fierce resistance from the established scientific community. Leading physicists, including Planck himself, insisted that light had to remain a wave during its journey through space, as centuries of elegant experiments involving interference, diffraction, and polarization had established wave optics beyond any reasonable doubt. Thomas Young had demonstrated light interference patterns with his famous double-slit experiment in 1801, and James Clerk Maxwell had unified electricity and magnetism into electromagnetic waves traveling at light speed. The evidence for waves was overwhelming, leaving physics trapped in a profound tension between wave and particle descriptions that seemed entirely irreconcilable. While Einstein was redefining the nature of light, a parallel revolution was unfolding regarding the internal structure of matter. Ernest Rutherford, working alongside experimentalists like Hans Geiger and Ernest Marsden, fired alpha particles at extremely thin sheets of gold foil to test the prevailing plum pudding model of the atom, which pictured positive charge as a diffuse cloud sprinkled with embedded electrons. Most particles passed straight through, but a small fraction bounced backward in a manner that Rutherford likened to firing artillery shells at tissue paper and having them return to hit the gunner. This stunning result proved that the atom possessed a tiny, incredibly dense central nucleus containing nearly all its mass and positive charge. Yet this discovery immediately triggered a catastrophic theoretical crisis for matter. According to classical electrodynamics, an electron orbiting a central nucleus is constantly undergoing acceleration as it curves through space, and accelerated electric charges must continuously radiate electromagnetic energy. An orbiting electron should rapidly bleed energy, spiraling inward and crashing into the nucleus within a tiny fraction of a microsecond. The fact that stable matter existed everywhere defied classical laws completely. Niels Bohr stepped into this vacuum in 19 Christian, proposing a hybrid model of the hydrogen atom that combined Rutherford's nuclear architecture with quantum restrictions. Bohr simply postulated that electrons could only inhabit specific, stable orbits without radiating energy, governed by the rule that their angular momentum must come in discrete, quantized multiples of Planck's constant, divided by 2 pi. When an electron transitioned between these allowed orbits, it emitted or absorbed a single photon whose frequency corresponded precisely to the energy difference between the states. This elegant rule successfully explained the mysterious spectral lines of hydrogen observed by experimentalists, showing that the unique color fingerprints emitted by heated elements were direct manifestations of quantized electronic transitions. Despite its incredible utility for simple systems like hydrogen, Bohr's model was ultimately an awkward bridge between classical orbits and quantum rules, failing when applied to multi-electron atoms like helium. The deeper question remained unanswered. If nature operated by such discrete rules, what foundational theory could unify these disparate observations into a coherent whole? The breakthrough came from an unexpected quarter when a young French aristocrat named Louis de Broglie submitted a doctoral thesis in 1924 proposing that if waves of light could manifest as particles, then particles of matter should likewise exhibit wave properties. De Broglie suggested that every moving particle has an associated matter wave, whose wavelength is determined by Planck's constant divided by the particle's momentum. While macroscopic objects like tennis balls have momenta far too large for their wavelengths to be detectable, microscopic particles like electrons possess wavelengths roughly comparable to the size of an atom. This audacious hypothesis provided a physical reason for Bohr's mysterious quantized orbits. An electron could only sustain a stable orbit if its matter wave wrapped around the nucleus cleanly, forming a standing wave that reinforced itself without destructive interference. When Clinton Davison and Lester Germer accidentally scattered electrons off a recrystallized nickel target at Bell Labs, they observed a sharp diffraction pattern that matched de Broglie's predicted wavelength with astonishing precision, proving experimentally that electrons could indeed behave as waves. As wave mechanics and matrix mechanics emerged from the subsequent work of Werner Heisenberg, Erwin Schrödinger, and others, the old world of classical certainty faded away. Reality at the microscopic level was revealed to be fundamentally probabilistic, defying simple visualization while offering a deeper, more accurate description of the universe. The strange journey from glowing ovens to matter waves demonstrated that nature operates according to rules far more subtle and magnificent than our everyday intuition could ever have anticipated, reminding us that the depth of reality stretches far beyond the surface of things we can easily touch and see. As the exploration of the subatomic realm deepened through the brilliant insights of Louis de Broglie and the experimental confirmations of electron diffraction by Clinton Davison, Lester Germer, and George Paget Thomson, the entire architectural framework of classical physics stood thoroughly dismantled and required an entirely new conceptual foundation to make sense of a universe where every solid particle carried an ethereal wave counterpart, and every smooth wave could behave like a discrete bullet of energy. This deep duality forced theoretical physicists into a period of intense intellectual labor during the mid 1920s, resulting in two distinct yet mathematically equivalent formulations of quantum mechanics that permanently altered how humanity perceives reality, starting with the revolutionary work of Werner Heisenberg, a young German physicist who approached the problem with a fierce, abstract determination to strip away any unobservable concepts from the language of physics. Heisenberg realized that since no one could ever directly see or photograph an electron orbiting inside an atom, any theory built upon precise orbital paths, positions, and velocities was indulging in philosophical fiction, leading him to construct a radically new mechanics based entirely on measurable quantities, like the frequencies and intensities of light emitted and absorbed by atoms, utilizing a mathematical tool known as matrices to represent physical observables in a way that discarded the traditional picture of particles traveling along continuous trajectories in space and time. While Heisenberg was constructing his esoteric matrix mechanics on the island of Heligoland while recovering from a severe bout of hay fever, an Austrian physicist named Erwin Schrödinger was taking a completely different, highly visual path inspired by de Broglie's matter waves, reasoning that if electrons were fundamentally waves, then there ought to be a wave equation that governs their behavior, just as Maxwell equations govern electromagnetic waves, leading him in early 1926 to write down his famous partial differential equation that treated the electron not as a tiny billiard ball moving on a track, but as a continuous wave function spreading out through space, evolving smoothly over time according to precise mathematical rules that could calculate the allowed energy levels of a hydrogen atom with breathtaking elegance and ease, instantly winning the adoration of physicists who preferred intuitive differential equations over Heisenberg's daunting matrix algebra. However, this apparent split between particle-oriented matrix mechanics and wave-oriented wave mechanics created a brief intellectual rivalry until Schrödinger himself proved mathematically that the two systems were entirely equivalent, two different languages describing the exact same underlying quantum reality. Yet this mathematical reconciliation only deepened the philosophical crisis because it left the physical interpretation of Schrödinger's wave function completely ambiguous, forcing Max Born to propose that the wave function did not represent a physical cloud of charge or matter spread out across space, but rather a probability amplitude whose absolute square gave the statistical likelihood of finding a particle at a particular location, introducing an irreducible element of chance into the heart of the natural world that horrified classical determinists like Albert Einstein, culminating in Heisenberg formulating his famous uncertainty principle in 1927, which established a fundamental unbreakable limit on how precisely certain pairs of physical properties, such as position and momentum, or energy and time, can be known simultaneously, not because measuring instruments are clumsy or imperfect, but because nature itself does not permit a particle to possess a definite position and a definite momentum at the very same instant, thereby shattering the Newtonian dream of a clockwork universe where knowing the exact state of every particle allows you to predict the entire future of the cosmos with absolute certainty. This profound shift in perspective was consolidated later that year at the historic Solvay Conference in Brussels, where the greatest minds of the 20th century gathered to debate the emerging Copenhagen interpretation championed by Niels Bohr and Werner Heisenberg, leading to legendary, deeply philosophical clashes between Bohr and Einstein over the nature of reality, complementarity, and whether an unobserved object can be said to possess definite properties before it is measured, arguments that forced physics to abandon naive realism and embrace an operational view where the act of measurement and observation cannot be cleanly separated from the system being studied, cementing a view of quantum mechanics that, despite remaining deeply counterintuitive and disturbing to our macroscopic human brains, has successfully survived nearly a century of rigorous testing without ever being proven wrong, governing everything from the stability of chemical bonds and the operation of semiconductors in computers to the nuclear reactions powering stars and the delicate technologies of modern quantum computing, demonstrating that behind the chaotic complexity of everyday experience lies a deeply unified mathematical tapestry governed by probabilities, quanta, and waves that continue to invite humanity into a deeper and more humbling appreciation of how astonishingly rich and strange the universe truly is. As the dust settled over the intense debates of the Solvay conferences and the physics community began to cautiously accept the strange probabilistic worldview forged by Bohr, Heisenberg, Born, and Schrödinger, a brilliant young British theoretical physicist named Paul Adrian Maurice Dirac entered the scene to solve one of the most glaring deficiencies of the new quantum theory, which was its complete incompatibility with Einstein's theory of special relativity, since Schrödinger's original wave equation treated time and space fundamentally differently, treating time linearly while treating spatial coordinates quadratically, prompting Dirac to embark on a quest to find a fully relativistic quantum wave equation that would respect the laws of relativity while still obeying the probabilistic demands of quantum mechanics. A mathematical challenge that seemed nearly impossible because any attempt to balance both first-order time derivatives and first-order spatial derivatives led to square roots of negative numbers and seemingly nonsensical negative energy states that would imply electrons could cascade downward into an infinite abyss of energy. Yet Dirac approached this terrifying mathematical anomaly with a breathtaking leap of imagination, proposing that these so-called negative energy states were not a flaw in his equations, but rather a profound prediction of an entirely undiscovered aspect of reality, suggesting that the vacuum of space was not an empty void, but a continuous sea of filled negative energy states known as the Dirac sea, where any missing electron, a hole in this sea, would manifest outwardly as a particle with the exact same mass as an electron but possessing a positive electrical charge, a stunning theoretical prophecy that was triumphantly confirmed just a few years later in 1932 when Carl Anderson discovered the positron while studying cosmic rays in a cloud chamber, marking the birth of relativistic quantum field theory and proving once again that the mathematical structures of quantum mechanics were far cleverer and more prophetic than the human minds that wrote them down. Even as physicists were still grappling with the philosophical implications of what it meant for a particle to pop into existence out of the vacuum, or to exist in multiple states simultaneously, a conceptual tension that reached its dramatic peak in 1935 when Albert Einstein, Boris Podolsky, and Nathan Rosen published a paper outlining what is now universally known as the EPR paradox, a brilliant thought experiment designed to demonstrate that quantum mechanics was fundamentally incomplete because it allowed for a phenomenon Einstein derisively referred to as spooky action at a distance, where two particles that interacted in the past and then separated by vast cosmic distances could remain entangled in such a way that measuring the state of the first particle instantaneously determined the physical state of the second particle, regardless of how far apart they were, violating the sacred relativistic speed limit that no signal or information can travel faster than light. An idea that Bohr and his followers countered by arguing that an entangled system must be treated as an indivisible whole rather than two independent objects existing in isolation, leaving the debate simmering as a philosophical curiosity for decades until a courageous experimental and theoretical physicist named John Stuart Bell stepped forward in 1964 to prove that this disagreement was not merely a matter of philosophical preference, but an empirical question that could be tested in a laboratory, deriving a mathematical inequality known as Bell's theorem, which established that if local hidden variables, the idea that particles carry pre-existing hidden instructions determining their measurement outcomes were true, then certain statistical correlations between entangled particles could never exceed a specific mathematical limit, setting the stage for a series of increasingly sophisticated experiments conducted over the following decades by pioneers like Alain Aspect, John Clauser, and Anton Zeilinger, whose rigorous laboratory tests consistently and overwhelmingly violated Bell's inequalities, proving beyond any shadow of a doubt that Einstein's local realism was fundamentally incorrect, and that nature at its core is irreducibly non-local, interconnected in ways that defy classical intuition and bridge the conceptual gap between abstract mathematics and concrete physical reality, while simultaneously laying the groundwork for a technological revolution that would completely reshape human civilization without most people even realizing it. Because the very electronic devices we use every day, from the semiconductor silicon chips powering our smartphones and computers to the lasers scanning barcodes at grocery stores, the atomic clocks synchronizing global positioning satellite systems, and the superconducting magnets used in magnetic resonance imaging machines in hospitals all rely directly on the principles of quantum mechanics, such as energy band theory, tunneling, and stimulated emission, proving that humanity's descent into the bewildering rabbit hole of subatomic strangeness was not just an intellectual exercise in abstract philosophy, but the practical master key that unlocked the modern technological world. And even today, as researchers push the boundaries further into the realm of quantum information science, developing quantum computers that exploit superposition and entanglement to perform calculations that would take classical supercomputers millennia to complete, and quantum cryptography protocols that use the act of measurement itself to guarantee absolute security against eavesdropping. The story of quantum mechanics continues to unfold with the same sense of awe, mystery, and profound discovery that gripped those few dozen scientists in heated debate a century ago, reminding us that every time we look closely enough at the universe, it responds by revealing layers of depth, beauty, and unity that far exceed our wildest imaginings, inviting us to forever look at the light falling upon our skin, not merely as a simple illumination, but as a shimmering, complex dance of waves and particles, echoing the deepest symphony of the cosmos. As the profound implications of quantum entanglement, Bell's theorem, and relativistic quantum field theory continued to reverberate through the hallowed halls of universities and research laboratories across the globe throughout the mid and late 20th century, the scientific community itself standing on a completely transformed landscape where the comforting clockwork certainty of Newtonian mechanics was nothing more than a historical footnote, replaced entirely by a sprawling, mathematically rigorous edifice of probabilities, complex Hilbert spaces, and non-local realities that challenged every single assumption our macroscopically evolved human brains could possibly muster about the nature of space, time, causality, and existence itself, prompting brilliant minds like Richard Feynman to famously declare that if you think you understand quantum mechanics, you don't understand quantum mechanics, a sentiment that did not discourage physicists from pushing forward, but rather served as a badge of honor and an invitation to delve even deeper into the bizarre operational machinery of the cosmos, leading Feynman himself to develop his revolutionary path integral formulation of quantum mechanics in the 1940s. A breathtakingly imaginative approach that discarded the traditional notion that a particle travels along a single definite path from point A to point B, proposing instead that an electron or a photon moving through space actually takes every single possible path simultaneously, from the straightest line to the most convoluted looping detour across the universe, with each path contributing a complex number called a phase. And when you add up all these infinite histories together, the phases interfere with one another constructively and destructively, causing all the wild, erratic paths to cancel each other out completely, while reinforcing the classical trajectory where the action is minimized. A concept so profoundly radical and counterintuitive that it initially sounded like pure mathematical fantasy, yet yielded the exact same experimental predictions as matrix mechanics and wave mechanics, cementing the triumph of equivalence and giving physicists an entirely new conceptual toolkit to calculate quantum electrodynamics with an astonishing precision that matched experimental measurements to 10 decimal places, a level of agreement between theory and experiment that remains unmatched in the entire history of human inquiry, and stands as a towering monument to the descriptive power of mathematics, when applied to realms far beyond direct human sensory experience, even as deeper theoretical challenges loomed on the horizon. Because while quantum mechanics had successfully conquered the microscopic worlds of atoms, electrons, and nuclei, and while special relativity had been successfully married to quantum theory via Dirac's equation and quantum field theory to explain the creation and annihilation of subatomic particles, there remained one colossal, stubborn wall that refused to fall, which was the total incompatibility between quantum mechanics and Albert Einstein's general theory of relativity, the master framework that describes gravity not as a traditional force pulling objects together through space, but as the smooth continuous curvature of four-dimensional spacetime caused by mass and energy, creating an agonizing theoretical schism at the very pinnacle of modern physics, because general relativity is inherently smooth, continuous, deterministic, and geometric, while quantum mechanics is inherently discrete, probabilistic, jumpy, and filled with fluctuations, meaning that when physicists attempt to apply the standard rules of quantum quantization to gravity, the equations inevitably blow up and yield nonsensical answers filled with infinite probabilities that cannot be renormalized away, presenting us with the ultimate unresolved mystery of contemporary science. A great conceptual chasm that divides our understanding of the universe into two radically incompatible languages, where the very large operates according to smooth geometric curvatures, while the very small operates according to chaotic probabilistic fluctuations, setting the stage for generations of theoretical physicists to embark on a grand, sweeping quest for a theory of quantum gravity, a unified framework that can seamlessly merge the macroscopic geometry of spacetime with the microscopic architecture of quanta, leading down fascinating and controversial paths, such as string theory, which replaces zero-dimensional point particles with one-dimensional vibrating strings of energy operating in 10 or 11 dimensions of spacetime, and loop quantum gravity, which proposes that spacetime itself is not a smooth, continuous background fabric, but is instead woven out of tiny discrete loops of quantized geometric area and volume, each approach offering tantalizing glimpses into a deeper reality while remaining maddeningly difficult to test directly in our current particle accelerators, because the energy scales required to probe the Planck length, the fundamental scale where quantum gravitational effects become dominant, are trillions of times higher than anything humanity can artificially produce, reminding us that we are still very much in the early chapters of our exploration of the cosmos, standing much like Max Planck did in 1900 at the precipice of a vast, uncharted ocean of discovery, forced to humble ourselves before a universe that stubbornly refuses to surrender its deepest secrets easily, yet continuously rewarding our curiosity with breathtaking vistas of mathematical beauty and profound conceptual unity that stretch far beyond the horizon of our everyday imaginations, illuminating the darkness of the unknown with the quiet, persistent glow of human reason, creativity, and wonder. These profound theoretical explorations into quantum gravity, string theory, and the discrete geometry of loop quantum gravity continued to expand the horizons of human thought. A completely new and revolutionary frontier emerged in the latter half of the 20th century and accelerated into the 21st, shifting the focus of quantum mechanics from abstract philosophical bewilderment and foundational physics toward the practical harnessing of quantum phenomena for computation, cryptography, and information processing. A paradigm shift known today as quantum information science, which fundamentally redefines how we view information itself by recognizing that information is not an abstract mathematical substance that exists independently of the physical universe, but is instead deeply and fundamentally physical, bound irrevocably by the strange rules of quantum mechanics, such that a bit of information in a classical computer, represented by a simple transistor being either firmly in a state of 0 or 1, is replaced in the quantum realm by the quantum bit, or qubit, a marvelous and delicate entity that can exist in a linear superposition of both 0 and 1 simultaneously, resting suspended in a complex probability space until the moment of measurement forces it to make a definitive choice, a property that allows quantum systems to process vast arrays of computational possibilities in parallel rather than sequentially, unlocking an exponential leap in processing power that makes classical supercomputers look sluggish by comparison. A theoretical realization first seriously championed by visionary physicists like Richard Feynman and David Deutsch in the 1980s, who understood that simulating quantum mechanical systems using classical computers was inherently inefficient because classical bits cannot naturally capture the intricate correlations and phase interferences of wave functions, whereas a computer built out of quantum components could simulate nature natively using nature's own rules, sparking a global race among physicists, engineers, and computer scientists to construct stable quantum processors capable of maintaining quantum coherence despite the relentless disruptive interference of the external environment. A monumental technological challenge because qubits are notoriously fragile and sensitive to even the slightest thermal fluctuations, electromagnetic stray fields, or atomic vibrations, which can cause decoherence and destroy the delicate quantum superposition before a calculation can be completed, requiring ingenious error correction codes and extreme cryogenic cooling environments colder than interstellar space just to keep the quantum states alive long enough to perform meaningful calculations. Yet, despite these formidable obstacles, researchers have successfully built working quantum processors with dozens and eventually hundreds of qubits, demonstrating quantum supremacy by executing complex computational tasks in seconds that would take the world's most powerful classical supercomputers thousands of years to finish, while simultaneously revolutionizing the field of secure communication through quantum cryptography, most notably via protocols like BB84, which utilizes the fundamental principles of quantum mechanics. Specifically, the fact that measuring an unknown quantum state inevitably disturbs it, to create encryption keys that are physically guaranteed to be secure against eavesdropping, because any attempt by a spy to intercept or measure the photons transmitting the key will leave an unmistakable statistical fingerprint that alerts the communicating parties immediately, rendering absolute security a law of physics rather than a mathematical assumption based on the computational difficulty of factoring large numbers, thereby transforming our technological landscape in ways that parallel or even surpass the invention of the transistor a century ago. All while these technological triumphs continue to force theoretical physicists to grapple with the oldest and most stubborn ghost haunting the house of quantum mechanics, which is the infamous measurement problem. The deeply unsettling question of what actually constitutes a measurement and how an objective, definite macroscopic reality can possibly emerge from a microscopic realm governed entirely by shifting probabilities and superpositions, leading to a colorful multiplicity of competing interpretations that attempt to make sense of the formalism without changing its predictive power, starting with the traditional Copenhagen interpretation formulated by Bohr and Heisenberg, which treats the quantum wave function not as a real physical object, but as a mathematical tool for calculating probabilities, asserting that a system has no definite properties until it is observed. A view that satisfies the pragmatic laboratory physicist who simply wants to calculate outcomes and get on with experiments, but deeply troubles those who wonder what happened to the universe before conscious observers evolved to look at it, prompting alternative views such as Hugh Everett's radical many worlds interpretation proposed in his 1957 doctoral dissertation, which takes the mathematical formalism of quantum mechanics at absolute face value and posits that the wave function never collapses at all, but rather that at every time a quantum measurement has multiple possible outcomes, the entire universe branches, splitting into parallel non-communicating realities where every single possible outcome actually occurs, meaning there is a universe where you read this sentence and another universe where you put down the text and went for a walk, an idea that sounds like science fiction, yet requires no arbitrary collapse mechanism and strictly obeys the linear Schrödinger equation, contrasting sharply with pilot wave theory, originally conceived by Louis de Broglie and later heavily expanded by David Bohm, which restores a comforting sense of determinism and particle reality. By proposing that particles do indeed have precise, definite positions and trajectories at all times, guided along their paths by a real physical pilot wave that propagates through space, introducing explicit non-locality, where every particle in the universe is instantaneously connected to every other particle through this guiding field. And more modern approaches like quantum Bayesianism or cubism, which adopts a radically subjective view of quantum states, arguing that the wave function does not represent a real physical property of the world out there, but rather quantifies an observer's personal degree of belief about future measurement outcomes, turning quantum mechanics into a normative guide for how a rational agent should update their subjective knowledge in the face of new empirical data. Each of these interpretations offering a different philosophical lens through which to view the mathematical machinery that Max Planck reluctantly unleashed upon the world back in 1900 when he sought to solve the trivial problem of why heated metal ovens glow with specific colors, reminding us that science is not merely a dry accumulation of facts and formulas, but a deeply human, imaginative journey into the unknown, a grand intellectual adventure that forces us to repeatedly abandon our comfortable, everyday intuitions about how reality ought to work and instead submit to the astonishing, beautiful, and sometimes bewildering ways the universe actually is, bridging the gap between the trillions of invisible photons washing over our skin in the quiet stillness of the evening and the vast, unfathomable cosmic architecture of galaxies, stars, and subatomic fields, leaving us ultimately with a profound sense of awe and humility as we realize that we are not passive, detached spectators looking at a distant clockwork machine, but active, conscious participants in a shimmering, deeply interconnected tapestry of waves, probabilities, and light that continues to invite our wonder, challenge our understanding, and whisper timeless secrets from the deepest heart of the cosmos. This is the domain of quantum mechanics, which is without question the most thoroughly tested and most flawlessly predictive scientific theory ever constructed. Yet at its core, it relies on concepts that feel fundamentally incompatible with reality itself. These are ideas that horrified the very geniuses who uncovered them. Ideas that sparked decades-long intellectual wars, ruined professional friendships, and forced generations of thinkers to redefine what it actually means to understand the universe. The quantum revolution did not happen in a blinding flash of single-day revelation, taking shape instead over 30 grueling years, forged by a tight-knit circle of scientists who were often simply trying to solve mundane, highly practical engineering problems. They wanted to know why ovens glowed different colors, why heated metals changed hue, and how light interacted with matter. And the answers they dragged into the light were so bizarre that many of them spent the remainder of their careers trying to disprove their own discoveries. To understand why reality feels so strange at the microscopic level, we have to travel back to the closing years of the 19th century, starting quite unglamorously with a problem about industrial furnaces. It was the late 1890s in Imperial Germany, an era of roaring industrial expansion where factories needed better illumination, lighting companies needed standardized bulbs, and the government was pouring money into empirical physics to secure a competitive edge in global manufacturing. At the center of this research was a seemingly innocent puzzle known as black-body radiation. Imagine a completely sealed hollow metal kiln, where stoking a fire beneath it heats the interior and causes the box to begin to glow. At first, it turns a dull cherry red, shifts to a blazing orange, brightens to a fierce yellow, and if you pump enough thermal energy into it, radiates a blinding white-hot glare. Blacksmiths had known this intuitive relationship between temperature and color for millennia, but by the 1890s, physicists wanted a mathematical law and an equation that could precisely predict the exact spectrum of light wavelengths pouring out of a heated cavity at any given temperature. Experimental physicists gathered pristine, gorgeous data curves with immaculate measurements. But the problem was that the theoretical physics of the day, classical mechanics and classical electrodynamics, the bedrock built by Isaac Newton, James Clerk Maxwell, and Ludwig Boltzmann, could not make sense of the data. In fact, when classical physicists applied their equations to the energy distribution inside the heated cavity, the math worked wonderfully for long wavelengths like the red and infrared end. But as calculations pushed towards shorter wavelengths and the ultraviolet end of the spectrum, the formulas broke down in a catastrophic fashion. According to classical theory, a heated box should emit an infinite amount of energy at short wavelengths, meaning that every time you turned on your kitchen oven under the laws of classical physics, it should instantly unleash a localized apocalypse of scorching ultraviolet radiation, vaporizing your kitchen and draining the universe of energy. Obviously, this did not happen, and your oven stays safely warm, leaving this embarrassing and fundamental collapse of classical physics christened as the ultraviolet catastrophe. It was not a minor rounding error or a missing mathematical term, but a total structural failure where two distinct formulas existed that flatly contradicted each other. Into this crisis stepped Max Planck, who was born in Kiel in 1858 and served as the intellectual embodiment of conservatism. He loved absolute order, revered the laws of classical thermodynamics as a sacred temple, and despised radical departures from tradition, making him the absolute last person on Earth who wanted to burn down classical physics. By October 1900, Planck had spent years wrestling with the black-body problem, and driven by sheer exhaustion and the need for a working solution, he presented a brand new formula to the German Physical Society that he had essentially interpolated by guessing an expression that smoothly bridged the existing conflicting formulas. When experimentalists checked it that very night, they found it was an exact match for reality across the entire spectrum, meaning Planck had the right answer, but he had no earthly idea why it worked. Over the next 2 months, Planck worked backward, desperate to find a theoretical derivation for his equation from first principles, and what he discovered horrified him because to make the math hold together, he had to assume that energy was not continuous. In the classical view, energy was smooth, flowing like water down a continuous ramp and infinitely divisible, but Planck discovered that to derive his formula, he had to assume that the atoms in the walls of the kiln could only emit or absorb energy in discrete, indivisible packets called quanta. These chunks were not all the same size because their energy was strictly proportional to the frequency of the light, meaning higher frequency light like blue and ultraviolet came in massive, punchy chunks, while lower frequency light like red and infrared came in tiny, gentle parcels governed by an exquisitely small number known as Planck's constant. Imagine a staircase versus a smooth ramp, where in everyday life energy looks like a ramp and you can stand at any arbitrary height. But Planck was proposing that at the atomic level, reality is a staircase, with steps just so infinitesimally small that in our macroscopic daily lives we cannot perceive the gaps. Though inside a high-temperature oven or at the scale of individual atoms, those steps matter immensely. At high frequencies, the steps of energy become so tall that atoms simply cannot muster enough energy to climb them, which is why the ultraviolet catastrophe vanishes, because the system lacks the capacity to spit out infinite high-frequency energy. Planck hated his own discovery, viewing the quantization of energy not as a profound revelation about the fabric of the cosmos, but as a desperate computational trick, a mathematical band-aid that he hoped future physicists would eventually strip away to reveal a proper classical explanation. Though he never found one, meaning the establishment had accidentally broken the universe open. If Planck opened the door with a trembling hand, a young man standing in Bern, Switzerland, kicked it completely off its hinges 5 years later in 1905 when Albert Einstein, a 26-year-old patent clerk with a wild mop of hair and a mind unbound by institutional orthodoxy, took a much bolder and more aggressive leap than Planck. Where Planck had treated quantization as a weird quirk of how matter emits and absorbs energy, Einstein proposed that light itself comes in chunks, meaning light was not merely an undulating, continuous wave traveling through space, but also a swarm of discrete particles or little bullets of energy later named photons, each carrying precisely one quantum of energy. To prove this, Einstein turned his attention to a stubborn experimental anomaly known as the photoelectric effect, which had been discovered by Heinrich Hertz in 1887 and occurred when ultraviolet light was shone onto a metal surface, causing the metal to eject electrons. According to classical wave theory, light was like ocean waves washing against a seawall. So if you turned up the brightness or intensity of a light wave, you were pouring more energy into the system. meaning classical physics predicted that a blindingly bright red light should easily knock electrons free, while a dim, ultraviolet light might take a long time to build up enough energy. Yet experiments showed the exact opposite, with a blindingly intense red light shining on metal forever without a single electron budging, while a remarkably dim ultraviolet light instantly knocked electrons free with fierce speed. Einstein realized that if light is made of particles, the mystery evaporates instantly because a single photon of ultraviolet light possesses a high frequency, meaning it packs a dense, heavy punch that transfers all its energy at once when it strikes a single electron. And if that punch crosses the threshold required to pry the electron away from the atomic lattice, out it flies, while the brightness of the light only dictates how many photons arrive rather than how much punch each individual photon carries. Red light, having a low frequency, carries weak individual photons, and no matter how many thousand weak photons you throw at the metal simultaneously, they do not pool their energy together like a mob because each photon acts entirely alone, meaning 1,000 weak punches cannot replace one knockout blow. Einstein published this revolutionary concept in 1905. During the same miraculous year, he also published his papers on special relativity and Brownian motion. And when he was finally awarded the Nobel Prize in Physics in 1921, it was explicitly for his work on the photoelectric effect, as a testament to how radical relativity still felt to the conservative scientific establishment. Yet, even Planck resisted Einstein's light particle hypothesis, because the wave theory of light was simply too successful, supported by Thomas Young's double-slit experiment from 1801 that had proven interference and diffraction, and James Clerk Maxwell's magnificent equations that had unified electricity and magnetism into electromagnetic waves, leaving seasoned physicists convinced that light was a wave and nothing else, and that the idea it could also be a particle felt like a regression to Isaac Newton's corpuscular theory, trapping physics in a profound identity crisis where light acted like a wave during propagation, but like a particle upon interaction. While the nature of light was being violently debated, attention shifted inward toward the architecture of the atom itself in 1911, when Ernest Rutherford, a booming and hands-on New Zealander working in Manchester, conducted a legendary experiment with his colleagues Hans Geiger and Ernest Marsden by firing high-speed alpha particles at a microscopic sheet of gold foil. Under the prevailing plum pudding model of the atom, which imagined positive charge as a diffuse, soft cloud with electrons scattered inside like raisins, the heavy alpha particles were expected to punch straight through with barely a wobble, and most did, but a tiny fraction of them bounced backward, ricocheting off the foil like cannonballs off tissue paper, leading Rutherford to famously remark that it was as if you had fired a 15-inch artillery shell at a piece of tissue paper and it bounced back to hit you. The conclusion was inescapable that the atom was not a soft pudding, and that almost all its mass and positive charge were packed into an incredibly dense, minuscule central core called the nucleus, while electrons orbited far away in vast expanses of empty space. This planetary model of the atom immediately triggered a catastrophic theoretical crisis, because according to classical electrodynamics, an electron orbiting a nucleus is undergoing constant circular acceleration, and accelerating electrical charges must continuously radiate electromagnetic energy as the foundational principle behind radio antennas. If an electron constantly radiates energy as it orbits, it should rapidly spiral inward, crashing into the nucleus within a fraction of a microsecond, meaning atoms should not exist and neither should you, your chair, or the stars above. Into this breach entered Niels Bohr, a brilliant and methodical young Danish physicist who in 1913 proposed a radical hybrid model of the hydrogen atom where he accepted Rutherford's nuclear model, but simply declared by fiat that classical physics did not apply at the atomic scale, postulating that electrons could only inhabit specific, stable, and non-radiating orbits as designated paths where they could circle indefinitely without losing energy. To determine which orbits were allowed, he borrowed Planck's quantum concept, stipulating that the angular momentum of an orbiting electron had to be quantized into whole number multiples of Planck's constant divided by 2 pi. When an electron dropped from a higher allowed orbit down to a lower one, it shed the excess energy by emitting a single distinct photon, whose frequency matched the exact energy gap between the two states. And when Bohr calculated the frequencies of light emitted by hydrogen based on this rule, the numbers matched experimental spectroscopy data with astonishing precision. For decades, scientists had known that heated elements emitted unique fingerprint-like lines of color rather than a smooth rainbow, but no one knew why until Bohr's model answered it instantly by showing that atoms emit discrete colors because electrons jump between discrete energy steps. However, Bohr's model was still a clumsy patchwork that worked brilliantly for hydrogen with a single proton and electron, but completely collapsed when applied to helium or multi-electron atoms, leaving lingering questions about why those specific orbits were stable and why electrons jumped instantaneously without traversing the space between, since Bohr had no answers and had simply nailed quantum rules onto a classical framework. The next great leap forward came not from studying particles harder, but from embracing a wildly audacious idea proposed by a French aristocrat named Louis de Broglie, who was born into a ducal family and initially studied history before falling in love with physics through his brother's work on X-rays. In his 1924 doctoral dissertation at the University of Paris, de Broglie posed a question of sublime simplicity by asking whether matter, which everyone assumed was strictly made of particles, should also behave like a wave if light, which everyone assumed was strictly a wave, could behave like a particle. De Broglie inverted Einstein's logic, arguing that if photons had a wavelength inversely proportional to their momentum, the exact same equation should apply to an electron, a proton, or even a bowling ball, meaning every moving piece of matter possessed an associated matter wave. For macroscopic objects like a tennis ball, the momentum is so massive compared to the unimaginably tiny scale of Planck's constant that the resulting wavelength is effectively zero, rendering wave behavior completely imperceptible. But for an electron, its mass is so minuscule and its speed inside the atom is so high that its de Broglie wavelength matches the actual physical size of the atom itself, making wave behavior the defining characteristic of electrons, rather than a minor footnote. This perspective instantly solved the mystery of Bohr's mysterious orbits, because if you imagine wrapping a vibrating string into a closed loop, where the circumference of the loop is an exact whole number multiple of the wave's wavelength, the wave reinforces itself to create a stable standing wave, whereas if it does not fit evenly, the wave destructively interferes with itself and cancels out. De Broglie realized that Bohr's allowed orbits were simply the specific radii where an electron's matter wave could form a stable, continuous standing wave around the nucleus, meaning quantization was not an arbitrary rule imposed from above, but a natural geometric consequence of electrons being waves. When de Broglie submitted this thesis, his committee was deeply skeptical and sent a copy to Einstein for evaluation. And Einstein immediately recognized its profound brilliance, remarking that de Broglie had lifted the corner of a great veil, which eventually led to de Broglie receiving the Nobel Prize in Physics in 1929. Theories soon met undeniable empirical reality in 1927 when Clinton Davison and Lester Germer, working at Bell Labs in New York, were firing beams of electrons at a nickel target and experienced an accidental laboratory accident involving a broken glass vacuum tube that oxidized the nickel, forcing them to bake the target at high temperatures to clean it, which unintentionally caused the nickel to recrystallize into large, orderly atomic lattices. When they resumed firing electrons at the baked nickel, they discovered something startling. The scattered electrons formed a clear diffraction pattern, which is an exclusively wave-based phenomenon that particles acting like billiard balls cannot reproduce, proving that electrons were bouncing off the crystal lattice like waves rippling through an obstacle, with measured wavelengths matching de Broglie's theoretical predictions to the letter. In a wonderful twist of scientific irony, George Paget Thomson, who was the son of J.J. Thomson, that had won a Nobel Prize for proving the electron was a particle, independently demonstrated electron diffraction by passing electrons through thin metal foils, meaning the father proved the electron was a particle, while the son proved it was a wave. And both were right in a universe that proved to be deeper, stranger, and far more wondrous than our everyday intuitions had ever dared to imagine. Building upon the profound realization that matter itself possessed a dual wave particle nature, the scientific community found itself standing at the precipice of an intellectual earthquake, knowing that the patchwork rules of Planck, Bohr, and de Broglie were merely stepping stones toward a much deeper, more radical mathematical reality. The mid 1920s became the crucible where modern quantum mechanics was forged, splitting briefly into two distinct paths before converging into a unified framework that would forever alter humanity's relationship with truth, certainty, and the physical world. The first of these paths was carved out by a young, intensely focused German physicist named Werner Heisenberg, who retreated to the desolate, pollen-heavy North Sea island of Heligoland in the summer of 1925 to escape a severe bout of hay fever, using the isolation to wrestle with the fundamental limitations of atomic models. Heisenberg realized that physicists had spent decades trying to build mental and mathematical pictures of things they could never actually see, such as the precise paths of electrons orbiting inside an atom, constructing elaborate models based on unobservable entities. He decided to abandon mechanical imagery entirely, choosing instead to focus solely on quantities that could, at least in principle, be measured in a laboratory, such as the frequencies and intensities of light emitted and absorbed by atoms. In place of ordinary numbers, Heisenberg utilized a branch of mathematics known as matrix algebra, where multiplying numbers together yielded different results depending on the order in which they were multiplied, meaning that position multiplied by momentum was not equal to momentum multiplied by position. When he returned from the island and showed his calculations to his mentor Max Born, Born stared at the strange rectangular arrays of numbers with a shock of recognition, realizing that Heisenberg had stumbled upon the matrix representation of quantum mechanics, a purely abstract, non-visual description of atomic phenomena that completely discarded the comforting classical notion of little billiard ball electrons traveling along neat, predictable tracks through space. While Heisenberg was banishing pictures from physics in favor of abstract algebra, an Austrian physicist named Erwin Schrödinger was taking the exact opposite approach, deeply inspired by Louis de Broglie's matter waves, and convinced that nature must be describable in terms of continuous, visualizable wave phenomena. Working in Zurich late in 1925 and into early 1926, Schrödinger sought a master wave equation that could govern the behavior of matter waves in the same way Maxwell's equations governed electromagnetic waves, or classical wave equations described ripples on a pond. By treating the electron not as a localized particle jumping between discrete orbits, but as a continuous wave vibrating around a nucleus, Schrödinger derived his famous wave equation, which described how a wave function, represented by the Greek letter psi, evolved continuously through space and time. For the physics community, Schrödinger's approach felt like a sudden, glorious return to sanity after the jarring abstraction of Heisenberg's matrices, because here was a differential equation that physicists already knew how to solve, offering smooth curves, familiar calculus, and a mental picture of waves spreading out and interacting without any sudden, inexplicable jumps. Schrödinger eagerly showed that his wave mechanics could solve the hydrogen atom problem just as cleanly as Bohr's old model, but with an underlying elegance that suggested the electron was truly a spread-out wave of charge rather than a microscopic planet. For a brief moment, it seemed as though physics might return to a comfortable, continuous wave-based reality, and Schrödinger openly expressed his disdain for Heisenberg's discrete, jumpy, unvisualizable matrices, hoping that the wave view would sweep away the clumsy corpuscular ideas once and for all. However, this intellectual harmony was short-lived because mathematicians and physicists soon proved that Heisenberg's matrix mechanics and Schrödinger's wave mechanics were mathematically identical, two different languages describing the exact same underlying reality, much like two people looking at the same object from different angles and seeing seemingly different shapes. Yet, the physical interpretation of Schrödinger's wave function remained deeply ambiguous, prompting German physicist Max Born to propose an interpretation that injected a profound element of chance into the heart of physics forever shattering the strict determinism that had reigned since the days of Isaac Newton and Pierre-Simon Laplace. Born suggested that the wave function itself was not a physical wave of matter or charge, but rather a probability wave, meaning that the absolute square of the wave function at any given point in space represented the statistical probability of finding the electron at that specific location if an observation were made. The electron was not literally smeared out across space like a cloud of mist. Rather, it was a particle whose future location could only be predicted in terms of probabilities, governed by a wave that dictated where it was likely to appear when forced to reveal itself. This meant that at the foundational level, the universe was fundamentally probabilistic rather than deterministic, governed not by absolute certainties, where identical causes produced identical effects, but by rolling dice on a cosmic scale where only statistical trends could be known in advance. This startling turn toward probability and indeterminism deeply disturbed Albert Einstein. The philosophical tensions reached their absolute peak in 1927 when Werner Heisenberg formulated what would become known as the uncertainty principle, a discovery that placed a fundamental unbreakable scheme of knowledge itself. Heisenberg realized that because subatomic entities possess both wave and particle characteristics, certain pairs of physical properties such as position and momentum, or energy and time, could not be simultaneously measured with absolute infinite precision, not because of clumsy laboratory instruments or poor experimental design, but because of the very nature of reality. If you design an experiment to pin down the exact position of an electron with extreme accuracy, you must use high-energy probes that inevitably disturb its momentum by an unpredictable amount, scrambling its velocity. Conversely, if you measure its momentum with great precision, its position becomes smeared out and uncertain. The more precisely you know where a particle is, the less you can know about where it is going, and vice versa, meaning that the classical dream of watching a mechanical universe unfold with absolute clockwork certainty was an illusion born of our macroscopic ignorance of the microscopic fuzziness underlying all things. The gathering of these brilliant minds at the Solvay conferences in Brussels during the late 1920s transformed into legendary intellectual battlegrounds where Einstein and Niels Bohr engaged in daily, deeply respectful yet fiercely intense debates over the meaning of quantum mechanics. Each morning at breakfast, Einstein would arrive with a clever thought experiment designed to expose an internal contradiction in quantum theory, imagining boxes leaking photons, clocks suspended by springs, and clever mechanical traps meant to trick the uncertainty principle. Only for Bohr to spend the day agonizing over the puzzle and returning by evening to demonstrate how Einstein's clever traps failed upon closer inspection. Bohr's position, known as the Copenhagen interpretation, argued that particles do not possess definite properties like position or momentum until they are actually observed or measured, treating the act of measurement as a fundamental boundary where the quantum realm collapses into classical certainty. To Bohr, asking what an electron is doing when nobody is looking was a meaningless question, because reality at the atomic scale is relational and participatory, bound irrevocably to the apparatus used to interrogate it. As these debates matured into the 1930s, the implications of quantum mechanics grew even stranger, prompting Schrödinger to devise his famous cat paradox in 1935 to highlight what he viewed as the absurd consequences of applying quantum superposition to everyday objects. Imagine a cat locked in a sealed steel box with a diabolical apparatus containing a tiny amount of radioactive substance, a Geiger counter, a vial of poison, and a hammer. If even a single atom decays over the course of an hour, the Geiger counter clicks, trips the relay, drops the hammer, shatters the vial, and kills the cat. According to the orthodox interpretation of quantum mechanics, until the box is opened and an observer looks inside, the radioactive atom exists in a superposition of both decayed and undecayed states simultaneously, which mathematically implies that the cat must also exist in a bizarre living-dead superposition of being both simultaneously alive and dead until the act of observation forces the wave function to collapse into one definite reality. Schrödinger did not invent this scenario to suggest that mystical, half-dead cats were roaming the world. Rather, He intended it as a scathing reductio ad absurdum to expose how incomplete and philosophically troubling the Copenhagen interpretation truly was when scaled up from single atoms to macroscopic creatures. Simultaneously, Einstein, alongside Boris Podolsky and Nathan Rosen, formulated the EPR paradox to challenge quantum mechanics from another angle, arguing that if the theory's description of reality was correct, it implied a deeply unsettling phenomenon they called spooky action at a distance. They pointed out that two particles could interact and then fly apart in opposite directions while remaining quantum mechanically entangled, meaning that measuring the state of one particle would instantaneously determine the state of the other, no matter how far apart they were separated, whether across a laboratory room, across the solar system, or across opposite ends of the observable universe. To Einstein, this instantaneous connection violated the absolute speed limit of the universe established by his own theory of relativity, which stated that no signal, information, or physical influence could travel faster than the speed of light in a vacuum. He believed this proved quantum mechanics was incomplete, missing some hidden variables that operated behind the scenes to predetermine the outcomes of measurements without requiring instantaneous telepathic links across space. For decades, this debate remained a philosophical stalemate, viewed by most working physicists as an untestable metaphysical disagreement that had no bearing on the practical application of the equations. However, the questions raised by entanglement and hidden variables did not remain purely philosophical forever, because decades later, theoretical physicists like John Stuart Bell formulated mathematical inequalities that allowed experimentalists to actually test whether local hidden variables could exist, or if nature truly embraced the non-local strangeness of quantum mechanics. In subsequent laboratory breakthroughs, particularly through the pioneering optical experiments of physicists like Alain Aspect, John Clauser, and Anton Zeilinger, Bell's inequalities were tested with entangled photons, proving conclusively that local hidden variables do not exist, and that nature at its deepest level is genuinely, undeniably non-local. The universe is woven together in ways that defy our everyday spatial intuitions, where distance is bridged by quantum correlations that mock the speed of light, confirming that the bizarre predictions of the early quantum pioneers were not mathematical errors or philosophical artifacts, but literal descriptions of how reality operates beneath the surface of our sensory experience. Today, the strange principles uncovered through those decades of reluctant discovery, industrial furnace problems, and fierce debates over ovens, light bulbs, and glowing gases have transformed from theoretical nightmares into the bedrock of modern technological civilization. Every time you unlock your smartphone using facial recognition, browse the internet over fiber optic networks powered by semiconductor lasers, or undergo a medical scan using magnetic resonance imaging, you are relying directly on the controlled manipulation of quantum states, energy bands, and probability waves that Max Planck and Albert Einstein reluctantly helped unleash upon the world. The quantum revolution taught humanity a humbling yet exhilarating lesson, demonstrating that our everyday intuition, forged in a macroscopic world of bouncing balls, falling apples, and rolling ramps, is merely a narrow parochial window onto a vast, deeply counterintuitive cosmos, where reality is far richer, stranger, and more unified than our ancestors ever dared to dream, reminding us that whenever we look closely enough at the fabric of existence, the universe gently insists that there is always another layer of depth, waiting to be understood by those brave enough to look past the surface. Building upon the triumph of quantum mechanics and its undeniable confirmation through Bell's inequalities and entanglement experiments, the mid-20th century ushered in an era where physicists no longer merely argued about the philosophical meaning of the quantum realm, but began to actively harness its rules to reshape the structure of modern science. The generation of thinkers who had wrestled with the conceptual nightmares of wave-particle duality, uncertainty and probability, wave collapse, passed the torch to a new breed of engineers, experimentalists and theoreticians, who treated quantum mechanics not as an existential crisis, but as a robust, highly operational toolkit. This transition from philosophical anxiety to practical mastery marked the birth of quantum engineering, solidifying the realization that understanding the discrete nature of energy levels and atomic interactions was the key to unlocking an entirely new epoch of human technological capability. To trace how this shift occurred, one must look closely at the evolution of solid state physics in the wake of the Second World War, a period where wartime radar developments and the urgent need for reliable electronics catalyzed a massive industrial push to understand the behavior of electrons inside crystalline materials. Classical physics could describe electricity as a smooth flow of charge through a wire, much like water through a pipe. But as engineers tried to miniaturize circuits and build faster, more dependable amplifiers to replace fragile, heat-generating vacuum tubes, they hit a wall that classical theories could not scale. The traditional model of conductors and insulators failed to explain why certain materials, such as silicon and germanium, acted as erratic middlemen, conducting electricity only under specific conditions when exposed to light or when spiked with microscopic impurities. The solution required bringing the full weight of quantum mechanics down to the atomic lattice, viewing solids not as continuous blocks of matter, but as vast, highly organized cathedrals of ions through which electron waves propagated in accordance with Schrödinger's equations. When theoreticians applied quantum wave mechanics to periodic crystal lattices, they discovered that electron energy levels inside a solid do not form a continuous smear, nor do they remain isolated like individual atoms. Instead, they broaden and merge into continuous bands of allowed energy separated by forbidden energy gaps. This band theory of solids provided the profound conceptual breakthrough needed to understand semiconductors, illuminating how electrons could be coaxed across a forbidden gap by thermal energy, light, or an applied electrical voltage. The boundary between a conductor and an insulator was no longer an arbitrary material property, but a direct consequence of quantum statistics and energy band structures. This realization did not remain confined to academic blackboards for long, as researchers at Bell Laboratories, including John Bardeen, Walter Brattain, and William Shockley, set out to engineer these quantum band gaps deliberately, culminating in the invention of the point contact transistor in late 1947 and the junction transistor shortly thereafter. The transistor, which won its creators the Nobel Prize in Physics, was the direct child of quantum mechanics, utilizing the controlled manipulation of quantum states in semiconductor materials to amplify and switch electrical signals without moving parts, high voltages, or vacuum tubes. The invention of the transistor triggered a relentless wave of technological miniaturization that would eventually define the modern digital age, transforming bulky room-sized computers fueled by vacuum tubes into sleek, pocket-sized microprocessors containing billions of quantum-engineered switches. As manufacturing techniques advanced, engineers learned to etch microscopic circuits onto silicon wafers, packing more and more transistors onto chips in accordance with Moore's law, until individual circuit components approached nanoscale dimensions, where classical physics broke down entirely and quantum phenomena could no longer be ignored. When insulating oxide layers in transistors become only a few atoms thick, electrons do not simply stop. They tunnel straight through the barrier via quantum mechanical tunneling, a phenomenon where particles possess a finite probability of passing through classically impassable energy barriers. Far from being a mere nuisance that plagued circuit designers, quantum tunneling became a vital mechanism utilized in flash memory, scanning tunneling microscopes, and advanced semiconductor architectures, proving that mastering the quantum realm was no longer optional for technological progress, but the absolute foundation upon which modern civilization rested. Simultaneously, the quest to understand how atoms interact with light at a quantum level led to another monumental breakthrough in the mid-20th century, the invention of the laser. In 1917, Albert Einstein had laid the theoretical groundwork by predicting a process called stimulated emission, wherein an incoming photon of a specific frequency could trigger an excited atom to release a second identical photon marching in lockstep with the first, creating a cascade of coherent light amplification. For decades, this remained an intriguing theoretical concept until researchers realized how to achieve a population inversion, forcing a majority of atoms into higher energy states rather than their relaxed thermal equilibrium. In 1960, Theodore Maiman successfully operated the first ruby laser, producing a narrow, intensely focused beam of monochromatic, coherent light, where every photon oscillated in precise phase alignment with all the others. The laser was a purely quantum mechanical device operating on the principle of discrete atomic energy level transitions and stimulated emission, and it swiftly revolutionized fields ranging from industrial manufacturing and telecommunications to precision medicine, eye surgery, and fundamental scientific research. As lasers and semiconductor technologies matured, physicists turned their attention toward harnessing the more subtle and counterintuitive aspects of quantum mechanics, particularly superposition and entanglement, to process information in ways that classical computers could never replicate. The foundational concept of classical computing relies on bits, binary digits that must exist in a definite state of either 0 or 1, much like a standard light switch that is strictly flipped either off or on. In the early 1980s, visionary physicists such as Richard Feynman and David Deutsch began exploring what would happen if information processing units were built to obey the laws of quantum mechanics rather than classical physics, noting that a quantum bit, or qubit, could exploit quantum superposition to exist in a linear combination of both 0 and 1 simultaneously. While a classical computer processes calculations sequentially or through massive parallel architectures by evaluating definitive states, a quantum computer utilizing multiple entangled qubits can explore a vast multidimensional computational space concurrently, evaluating complex probabilities and interference patterns that allow certain classes of problems to be solved exponentially faster than the most powerful supercomputers ever built. Building a functional quantum computer, however, required overcoming monumental experimental hurdles that pushed human engineering to its absolute limits because quantum states are notoriously fragile and easily disrupted by their surrounding environment. When a fragile superposition interacts with stray magnetic fields, thermal fluctuations, or ambient radiation, it undergoes a process known as quantum decoherence, wherein the delicate phase relationships that bind the superposition together leak into the environment, causing the quantum information to degrade into classical noise within microseconds. To combat decoherence, experimental physicists had to invent extraordinarily sophisticated isolation techniques, cooling superconducting quantum circuits down to temperatures colder than deep space inside dilution refrigerators, constructing elaborate vacuum chambers, and designing error-correcting codes that could protect vulnerable qubits by distributing quantum information across multiple physical components. Various competing hardware architectures emerged, ranging from superconducting circuits and trapped ions held in laser cages to topological qubits and photonic systems, each striving to achieve quantum supremacy. The threshold where a programmable quantum device successfully solves a highly specialized computational problem that is practically impossible for any classical supercomputer to finish within a reasonable time frame. Beyond computation, the deliberate exploitation of quantum entanglement gave rise to the field of quantum cryptography and secure communications, solving ancient problems of confidentiality by anchoring encryption keys to the unyielding laws of physics rather than computational complexity. In classical cryptography, secure communication relies on mathematical algorithms that are difficult to crack, such as large number factorization, but which remain theoretically vulnerable to advances in computing power or mathematical breakthroughs. Quantum key distribution, pioneered in the 1980s by Charles Bennett and Gilles Broussard, utilizes individual photons to transmit cryptographic keys between communicating parties in such a way that any unauthorized attempt by an eavesdropper to intercept or measure the photons inevitably disturbs their quantum states via the uncertainty principle, instantly alerting the legitimate users to the breach. This unconditional security, guaranteed by the fundamental laws of nature rather than the limits of human computing machinery, transformed quantum communication from a theoretical curiosity into a rapidly expanding global infrastructure of secure satellite networks and fiber optic distribution systems. Furthermore, the sensitivity of quantum systems to external perturbations inspired the development of quantum sensors and metrology, enabling unprecedented levels of precision in measuring time, gravity, magnetic fields, and spatial orientation. Atomic clocks, which serve as the beating heart of global positioning systems, telecommunications synchronization, and fundamental physics research, operate by measuring the exact microwave frequency required to induce a quantum transition between two energy levels in atoms like cesium or strontium, achieving stability so extraordinary that modern optical lattice clocks would neither gain nor lose a single second over billions of years. Similarly, quantum magnetometers and gravimeters utilize superconducting quantum interference devices and entangled atomic vapors to detect microscopic fluctuations in magnetic fields and gravitational pulls, opening new windows into neurological brain imaging, subterranean mineral exploration, and the detection of gravitational waves rippling through spacetime from distant cosmic collisions. The journey from Max Planck's reluctant mathematical patch in 1900 to the sophisticated quantum technologies of the 21st century reveals a profound truth about the human endeavor to comprehend reality. The universe is infinitely deeper, more interconnected, and more magnificent than our macroscopic intuitions could ever have anticipated. Every time we peer into the quantum domain, we are reminded that the weirdness of nature is not an obstacle to be bypassed, but the very foundation upon which existence is built, inviting us to continue exploring the endless layers of depth waiting quietly beneath the surface of the everyday world. Beyond the realm of practical engineering and commercial quantum technologies, the deep mysteries that troubled Einstein and Bohr nearly a century ago continue to drive the most ambitious theoretical pursuits in modern physics. The crowning triumph of quantum mechanics, its unmatched empirical success in describing the microscopic domain of atoms, quarks, and photons, stands in stark, frustrating contradiction to the other great pillar of 20th century physics, Albert Einstein's general theory of relativity. While quantum mechanics reigns supreme in the microscopic realm of the extremely small, governing the forces of subatomic particles with probabilistic grace, general relativity rules the macroscopic cosmos of the extremely large, describing gravity not as an invisible pull but as the smooth, continuous warping of space-time caused by massive stars, planets, and galaxies. These two intellectual edifices speak entirely different languages, utilize incompatible mathematical frameworks, and treat the fabric of the universe in mutually exclusive ways, creating a profound theoretical schism at the heart of modern science. General relativity treats spacetime as a smooth, continuous, predictable stage upon which the cosmic drama unfolds, where geometry is unbroken and deterministic down to the smallest scale. Quantum mechanics, by contrast, reveals a frantic, turbulent, and fundamentally probabilistic micro-realm where empty space is never truly empty, but instead a churning sea of quantum fluctuations, virtual particles flickering in and out of existence, and unresolvable uncertainties. When physicists attempt to apply the mathematics of quantum mechanics to the gravitational field itself, seeking to quantize gravity and understand the subatomic behavior of spacetime, the equations break down, yielding nonsensical infinities that signal a catastrophic breakdown of our theoretical understanding. This failure becomes most acute and unavoidable in places where immense mass is crammed into infinitely small subatomic volumes, such as the singular heart of a black hole or the blistering, hyperdense ignition point of the Big Bang at the dawn of the universe. To resolve these paradoxes and forge a unified theory of quantum gravity, physicists have spent decades exploring radical hypotheses, from the multidimensional vibrating energy strings of string theory and M theory to the discrete quantized spatial loops of loop quantum gravity, each attempting to stitch the smooth continuous geometry of Einstein's cosmos together with the granular, choppy pixelation of the quantum world. Alongside the quest for a final unified theory, the philosophical interpretations of quantum mechanics have continued to evolve, forcing thinkers to confront the deeply unsettling implications of measurement and reality. While the pragmatic Copenhagen interpretation embraced the idea that particles do not possess definite properties until observed, it left open a Pandora's box of conceptual difficulties concerning what constitutes an observer, how a wave function actually collapses, and whether consciousness plays a fundamental role in shaping physical reality. To escape these philosophical quandaries, alternative interpretations have flourished over the decades, offering vastly different visions of what the math is telling us about the universe. Hugh Everett's many worlds interpretation, initially dismissed when proposed in his 1957 doctoral dissertation, suggests that wave functions never truly collapse at all. Instead, every time a quantum measurement has multiple possible outcomes, the entire universe branches, resulting in a branching multiverse, where every alternative history and potential reality actually happens in its own segregated, uncommunicating parallel timeline. Meanwhile, pilot wave theories, championed originally by Louis de Broglie and later expanded by David Bohm, rescue visualizable trajectories by positing that particles really do have precise positions and paths guided along by a literal physical pilot wave, sacrificing local realism to preserve determinism. Other frameworks, such as objective collapse models, propose that wave functions naturally and spontaneously collapse when a certain threshold of mass or complexity is reached, bridging the microscopic and macroscopic worlds without requiring human intervention or infinite branching universes. The persistence of these competing interpretations reminds us that science is not merely a static collection of settled facts, but an ongoing, deeply human adventure in deciphering a reality that continually subverts our simplest assumptions. From Max Planck's desperate mathematical trick in an industrial furnace to Einstein's revolutionary photons, from Rutherford's gold foil experiments to de Broglie's matter waves, and from the strange computational power of qubits to the cosmic mysteries of quantum gravity, the story of quantum mechanics is a testament to the staggering power of human curiosity. It teaches us that nature is not obliged to conform to our everyday intuitions, and that true understanding often begins at the exact moment our comfortable certainties shatter. As we look toward the horizon of future discoveries, peering deeper into the quantum vacuum and building technologies that manipulate the very building blocks of existence, we do so with the humbling awareness that the universe is infinitely richer, stranger, and more wondrous than we can possibly imagine, and that we have only just begun to read the opening chapters of reality's grand and mysterious book. This deep interconnection between the smallest constituent parts of matter and the grandest scales of astrophysics reveals one of the most astonishing realizations of modern science. The universe is a profoundly unified whole. The nuclear fusion reactions burning inside the core of distant stars, lighting up galaxies across billions of light years, are fundamentally governed by the same quantum tunneling and discrete energy transitions that physicists manipulate in microchips on Earth. Astronomy and quantum mechanics, once thought to occupy opposite ends of the scientific spectrum, are in reality two sides of the same cosmic coin, bound together by laws that do not care about our arbitrary human distinctions between the microscopic and the macroscopic. Looking back over the arc of this intellectual journey, from the darkened industrial laboratories of late 19th century Germany to the sterile, ultra-cold dilution refrigerators of contemporary quantum computing facilities, we see a recurring pattern in the history of human thought. Whenever our models of reality have seemed complete, whenever we have convinced ourselves that the final laws of nature were nearly in our grasp, the universe has a way of introducing a new anomaly, a stubborn contradiction that forces us to abandon our comfortable assumptions and climb to a higher plane of understanding. The quantum revolution was not merely a technical upgrade to our tools or a localized adjustment to our equations. It was a profound ontological awakening that taught us humility, reminding us that objective reality does not bend to our everyday intuitions, but instead operates according to rules of staggering subtlety, elegance, and beauty. As we stand today on the threshold of a new technological and scientific era, peering into quantum vacuums, probing the nature of entangled space-time and engineering devices that exist in multiple computational states simultaneously, we carry forward the legacy of those reluctant revolutionaries who first dared to imagine a quantized world. Max Planck, Albert Einstein, Niels Bohr, Louis de Broglie, Werner Heisenberg, and Erwin Schrödinger did not set out to shatter the classical framework of physics. They were simply trying to answer honest questions about the world around them. In doing so, they opened a door that can never be closed, inviting every subsequent generation to look past the superficial appearance of everyday objects and marvel at the hidden, dancing machinery of the cosmos, where reality reveals its deepest secrets only to those willing to embrace the wonderful, bewildering strangeness of the universe. And so, as we peer further into the 21st century, this ongoing evolution of quantum science brings us full circle to the very mystery that opened our story. We began with trillions of invisible photons washing over our skin, carrying the dual heritage of waves and particles across the silent expanses of space. We traced that path through the frantic industrial ovens of Berlin, the quiet patent office desks of Bern, the explosive gold foils of Manchester, and the frozen dilution chambers of modern quantum laboratories. What we have discovered along the way is not merely a set of clever engineering principles or esoteric mathematical equations. We have discovered a fundamental truth about our relationship with the cosmos. For centuries, classical physics encouraged a detached, spectator view of reality, portraying the universe as a giant, independent clockwork mechanism ticking along indifferent to our existence, while we humans stood safely outside the glass, watching the gears turn. Quantum mechanics shattered that illusion forever. By revealing that the act of measurement alters the system, that particles do not possess definite properties until interrogated, and that distant entities remain invisibly entwined across the void through entanglement, quantum theory invites us into a vastly more intimate, participatory universe. As the visionary physicist John Archibald Wheeler famously suggested, we are not merely passive observers standing on the outside looking in. We are active participants helping to shape the very reality we seek to understand. This realization transforms our place in the grand tapestry of existence. The weirdness of quantum mechanics is not a bug in the code of nature, nor is it a temporary puzzle waiting to be swept away by a return to classical comfort. It is the signature of a deeper, richer reality, a reminder that the universe operates on a scale of subtlety and interconnectedness that dwarfs our everyday imaginations. Every time a modern quantum computer calculates complex molecular simulations to discover life-saving medicines, every time an atomic clock synchronizes global communication across continents with unimaginable precision, and every time a curious mind pauses to wonder at the strange, shimmering duality of light, we are honoring the legacy of those reluctant revolutionaries who dared to follow the math wherever it led. The story of the quantum is, at its heart, the story of human courage in the face of the unknown. It proves that whenever we are willing to go of our comfortable assumptions, whenever we stare unflinchingly at an impossible anomaly, like the ultraviolet catastrophe or the photoelectric effect, the universe rewards our curiosity by opening doors to realms we never knew existed. And as we continue to push forward into uncharted technological and philosophical frontiers, decoding quantum vacuums, wrestling with the unification of gravity, and building machines that think in superpositions, we do so with the enduring, humbling recognition that reality is infinitely deeper, more mysterious, and more magnificent than we have ever dared to dream.